Hi everyone, welcome back. Today we'll be talking about trig substitution. This is much different than trig integrals, and it will help you solve integrals of the form something over the square root of a squared plus or minus x squared, where a is some number like 1, 2, 3, for example. And the idea here is that we can recognize, the square root of a squared plus x squared, for instance, as being part of a Pythagorean theorem. And we can also do the same with a squared minus x squared and x squared minus a squared, right? So they're all part of this right triangle business that we're pretty familiar with. And so what we can do is we can imagine all the different possible scenarios. So I can have, for instance, an x squared plus a squared term, which tells me that that would have to be the hypotenuse if x is over here and a is over there, right? So we're just using a squared plus b squared is equal to c squared, and we're writing our third side in terms of x and a. Okay, so if we do that then, remember I can now describe this triangle using an angle theta, and two different legs of the triangle. And so I can rewrite this as tangent of theta is equal to x over a, right? That's a true statement. And it tells me that x is equal to a times tangent of theta. Okay, so just naturally, this is a substitution we'll want to make our lives easier. Right now, it's very abstract, right? But once we do examples, we'll see exactly why writing x is equal to a tangent of theta will actually help us out. Okay, another scenario we can have is the square root of a squared minus x squared, which means that a has to be along the hypotenuse and x along this leg over here. What we end up getting is that sine of theta is equal to x over a, which again is a true statement, which means we can write x is equal to a times sine of theta. And again, we'll see why that's helpful to do. And the very last one is involving cosine of some sort, right? So we have the square root of x squared minus a squared over here, which means that x needs to be along my hypotenuse and a needs to be the leg down here. What this means then is I can write cosine of theta is equal to a over x, but notice here I have to solve for x. This says x is equal to a over cosine theta, which means x is equal to a secant theta. Okay, so notice that there's nothing really stopping me from switching these two, right? I can put a over here and the square root of x squared minus a squared down here, but just trust me that the math works out better if you do it in terms of secant instead of cosine. Okay, so now that we've made the substitutions, we can go ahead and do an example. And we'll kind of walk through the steps of what each problem should look like. So we have this problem here, the integral of x dx over the square root of 9 plus x squared. And we've seen integrals like this before, and we can actually do them without using trig sub, right? So I have an x squared here, and I have an x here. So this is a simple use substitution problem. But I want to show you how we can solve it using trig sub. And we'll get in the habit of doing it this way in the future. So what we want to do, I need to put x is greater than 0 here. But what we need to do first is draw our triangle specific to this problem. So I go up here and I recognize the square root is of the form a squared plus x squared. So I go up here and I recognize it as this triangle here. So immediately what a lot of people like to do is say x is equal to a tangent of theta and go on their way. That's totally fine, but I'm going to work it out specific to this triangle. So that tells us that we have a, which is 3 down here. I have x over here, and I have the square root of 9 plus x squared as my hypotenuse. We can go ahead and work this out. This says that x is equal to 3 tangent of theta. And then what we need to do is we not only need to solve for x, but we need to solve for dx as well. So that's a common mistake here, but we need to differentiate this. Dx is equal to 3 secant squared of theta, d theta. And then essentially what we can do is we can substitute everything in here now. I'd like to do one more step, and it's to figure out what the square root is going to be equal to. And this is where it's actually really helpful to see why we substituted 3 tangent theta in the first place. So I'll do it out here. I need to solve for x squared, which gives me 9 tangent squared of theta. I need to add 9 to that, which is 9 plus 9 tangent squared theta. This might be painstakingly slow, but I can factor out that 9. 1 plus tangent squared of theta. And what I'm left with then, this right here is a trig identity. And this will leave me with a perfect square. This is equal to 9 secant squared of theta. So then if I take the square root of both sides, I have the square root of 9 plus x squared is equal to just simply 3 secant of theta. Okay, so that's why we chose this in the first place. We found that through a trig identity here, we're able to get our square root down to simply one trigonometric function. And we'll see it often cancels with stuff on the top. So we can go ahead and finish out this integral. After I substitute everything in terms of theta, I get the integral x is equal to 3 tangent theta, dx is equal to 3 secant squared theta d theta. And on the bottom, that whole square root stuff actually turns into just 3 times secant theta. So I can cancel 1 on top with 1 on the bottom. This 3 will cancel with that. And I'm left with 3 integral of secant theta tangent theta d theta. And we know how to do this integral, right? This is simply 3 secant of theta and plus c. Another pitfall is that we're not quite done yet, right? So they gave me my function and my integral in terms of x. I better give them an answer in terms of x. So this is where drawing the triangle first really comes in handy. I need to figure out what secant of theta is based on this triangle that we drew. So we know that secant is 1 over cosine. And we know we can figure out what cosine is pretty simply. Cosine of theta in this triangle here is equal to 3 over the square root of 9 plus x squared, which tells me that secant of theta is just a reciprocal of that, square root of 9 plus x squared over 3. And then we simply get that our integral of x dx over the square root of 9 plus x squared is equal to 3 times this, so this 3 will cancel, and I'm left with 9 plus x squared plus c. Okay, so I know this was more involved than just doing the u substitution, but I think it's a good example to get started. Let's go ahead and do another one. We have the integral of x cubed dx divided by the square root of x squared minus 1. So here you're really stuck, right? There's no real u substitution you can make. You can try making u x cubed, but then your du is under a square root. That's not going to be super fun to work with. So let's try using trig sub. Again, we want to draw the triangle as specific to our case as we can. So we go up and we see which case resembles the square root that I'm working with. So I have x squared minus 1. And if I go up here, that looks a lot like this one, right? So I go ahead and I set my hypotenuse length equal to x. I have the square root of x squared minus 1, and I have 1 right here. The substitution they told me to make then is that x is equal to a times secant of theta. A in our case is 1. So x is equal to secant of theta. Again, don't forget to do dx. We get secant theta tangent theta d theta. And then again, you can substitute everything in if you'd like. I like to get rid of the square root all on its own. So x squared is equal to secant squared of theta. X squared minus 1 is equal to secant squared theta minus 1. We know that to be equal to tangent squared of theta based on that identity. So when I take the square root of both sides, I found that my square root is simply equal to tangent of theta. And of course, you have to pay attention to which values of theta are allowed. That's more of a subtlety, so I won't really talk about it too much, but it is important to note that that's there. And finally, we can substitute everything in. So I have the integral now becomes secant cubed, so that's x cubed. And then dx is secant theta tangent theta d theta. Divide that by simply tangent theta. And you see that these cancel out. And we get that this is equal to secant theta to the 4th power, which isn't a super great integral, but we did work it out in a previous trig integral video. So I'll go a little bit less thorough through it, but essentially what we end up with is the integral of 1 plus tangent squared theta secant squared theta d theta. So I turn one of these secant squareds into a 1 plus tangent squared through the identity. I can split this up into the integral of secant squared theta d theta plus the integral of tangent squared theta secant squared theta d theta. And then again, really quickly, this is an elementary integral, right? So this is simply tangent. This right here is a u substitution, right? So I have the derivative of tangent here, and I have tangent itself. So this gives me plus a third tangent cubed of theta plus c. And again, I'm not done, right? So I need to rewrite this in terms of x. What I can do is I can go back up to my triangle and figure out what tangent of theta is. Tangent of theta is opposite over adjacent. So it's the square root of x squared minus 1 over 1, which is just the square root. And so I can substitute that back in now. This will give me the square root of x squared minus 1 plus a third times x squared minus 1 to the 3/2 plus c. Great. Okay, and this is my final answer here. I'm done. If I had bounds, I'd have to plug them in. But essentially, this is how you're going to go through and solve these types of problems. Again, I'd recommend drawing a triangle right off the bat. And then I'd also recommend, if you're still getting the hang of it, doing all of these substitutions that I did here outside of the integral. And then everything will cancel right away instead of you having to mess around with the square root and stuff. Okay, so I hope this was a good review of trig substitution.